Greetings everybody, and today we're going to be evaluating this improper integral running from minus infinity to infinity of x over sinh of x. So I've done something fairly similar in the past on this channel. That was the integral of the hyperbolic secant, and for that we used a rectangular contour, and we're basically going to be using the same approach today, just with a little bit of a modification. And you would have seen the contour we're going to be using in the thumbnail of this video already. But yeah, let's just jump straight into it. We're going to first of all define a complex function f of z to be equal to the integrand, but we replace all the x's with the z's, and I'm also going to replace a sinh with its exponential definition, so that's e to the z minus e to the minus z divided by 2, but we can flip that up to the top. So that's our function f of z. We're going to be contour integrating, and now notice this sinh function actually has some zeros, which means we're going to have poles on our integrands. In particular, we want to solve for where sinh of z is equal to 0. And well, on the real line at least, there's only one zero, namely that's z equals 0. But in the complex plane, there's actually infinitely many zeros along the imaginary axis. And to see where exactly they are, well, remember there's a relationship between sinh and sine. If you multiply by an I out here, then this is the same as the sine, but you put the I inside of the argument. It's sine of iz. So we're solving for where sinh equals 0, which means we need to solve for where sine of iz equals 0. Iz, we know where sine of something is equal to 0. In particular, we want iz to be equal to integer multiples of pi, so k times pi. But now we want to solve for z. That's nothing too tricky to do. Just multiply both sides by minus I, and you'll get something like minus I times k times pi. But really that's just I times k times pi, because after all, k is just an integer. So we know where the poles are. The poles are going to be at k times I times pi. So if we draw out a little bit of picture of the complex plane, this is what we should get. So we have poles at 0, I times pi, minus I times pi, and they continue infinitely along the imaginary axis. Now, this pole at 0, that's actually going to be a removable singularity, because if you take the limits on our integrand as we approach 0, we can assign the value of 1. So if you take the limits, use L'Hopital's or something, you're going to get 1. So this function, as it is, it's undefined at 0, but we can assign a value at z equals 0 to make it holomorphic. So technically, we can just forget about this pole, because everything is nice and holomorphic there. So this is a removable singularity. So this is going to help us construct our contour, because our interval of integration is going from minus infinity to infinity. So we want to start at some, let's say, r value, minus r, and go up to some capital R over here. And so we want our line integral to go along this path on the real axis. And yeah, we can cross through that singularity there, because technically there's no singularity there. So this is what we want to integrate along this path. Now we want to turn this into a contour. We can use a semicircular upper arc. However, if we take r to infinity, we're going to enclose infinitely many poles, and that's not a really good thing in this case. Let's just deal with one pole, and the way we do that, we're just going to go up a finite amount and then construct a path going backwards. So we go up over here, then we go backwards. Now we're going to run into this pole over here, the singularity. Now there's two ways to go about this. We can go above or we can go below. Now going above, we would have to use the residue theorem and then also evaluate the integral along that upper arch. However, if we go below, notice we don't have to use the residue theorem anymore, because by Cauchy's integral theorem, the whole entire contour will just evaluate to 0, because everything is nice and holomorphic inside. So this is the contour we're going to be working with. Let's call the paths up here sine 1, sine 2, and the paths on the side of the psi 3 and psi 4, and we'll call the whole entire contour C, and that singularity that's I times pi. So this is the setup that we have so far. Let's write down a couple of integrals. So first of all, we have the contour integral over C. We know that's going to be equal to 0, but we can decompose the contour integral over C into each of its individual parts. So that's the integral over sine 1 plus sine 2 plus psi 3 plus psi 4. And then we also have the integral over, well, on the interval minus r to r. And then we also have the integral along this little semicircle path that I call gamma. Okay, so these are all the integrals we're going to be evaluating. The integral from minus r to r, that's obviously in the limits going to become the integral we want to evaluate, which is I over here. So in the limits, this is just going to reproduce I. The integrals along psi 1 and psi 2, these are also going to recover our integral I in some way. The integrals over psi 3 and psi 4, however, those are the integrals on the side, and actually as you push them further and further out, these are going to vanish, so we'll show that later. And we also have the integral over gamma, but we'll need to treat this one with a bit of care, I think. So this is the general idea so far. Let's go onto the right hand side of this whiteboard and we'll start evaluating some integrals. I'm going to start with the integrals over psi 1 and psi 2, and we'll do them together. So the integral over psi 1 plus the integral over psi 2. Now, how do we do these two integrals? Well, I'm going to introduce a parameterization on the integral on psi 1. Actually, both of them, this would work actually. So we're going to introduce the parameterization z equals, now what's happening on psi 1 and psi 2, our imaginary part is pi. So we're going to have I times pi, and then we're varying our real part, so we're going to have a parameter t in here, so t plus I pi, and yeah, we're going to have different domains for t depending on psi 1 and psi 2. Okay, so if we plug this in over here, and also dz is going to be equal to dt, of course, so let's plug this in. So for psi 1, well, we're going to start at some minus epsilon over here, and then go out to this corner. So this corner is minus r plus I times pi, and yeah, we're just going to start a little epsilon away from I pi. And this corner out here, that's also r plus I pi. So we're going to go from minus epsilon to minus r, and we're going to plug this parameterization into our function. So that's going to be 2 t plus I times pi divided by e to the t plus I times pi minus e to the minus t, and then we also have minus I times pi. And then dz was equal to dt. Okay, and then we also have a plus the integral over psi 2, but we can plug in the same parameterization. Now we're starting at r and running back to epsilon. So we're going to have r back to epsilon of 2 t plus pi. Okay, so now what I'm going to do, notice we have these I pi's everywhere. What we can do is split up the exponential, and we'll get e to the I pi and e to the minus I pi everywhere. But notice those evaluate to minus 1, and we can factor out those minus 1s there and use them on our integrals. So distribute it into our integral, and what that allows us to do is flip the bounds because the orientation is a little bit funny at the moment. So what does this give us? So we're going to get the integral, flipping the bounds, we're going to end up having the integral from minus r to minus epsilon, and what we'll do as well, I'll distribute over here, and what that gives us is 2t plus 2 pi I over e to the t minus e to the minus t, and then dt, and then basically the same thing over here. We flip the bounds, so epsilon to r. Okay, so now notice these integrands are the same, so we can combine these intervals of integration together, and what we're going to get is the integral running from minus r to minus epsilon, union epsilon to r, and I'm also going to split up the integrals, split up the fractions as well, and we're going to get 2t divided by e to the t minus e to the minus t dt, and then we also have plus 2 pi I here. I'll just write maybe pi times I out the front, and then we have the integral over the same interval here, so minus r minus epsilon, and then union epsilon to r of, that's going to be 2 over e to the t minus e to the minus t, but notice this guy over here, that's just 1 over sinh. So we have 1 over sinh of t dt. Okay, so now this is what we have. Let's take the limits as r approaches infinity and epsilon approaches 0. Notice on this interval, we're basically going to be integrating from minus infinity to infinity of this guy, but this is basically our original function here. So this just recovers I in the limit. And now as for the second integral, this gets a little bit more technical because we still have this plus pi times I. However, if you take the limits as these epsilons approaches 0, if you take a look at the sinh function, well, it has a 0 right at t equals 0. And that becomes problematic when you take the reciprocal, because what happens, I think the function blows up, so it does probably something like this, kind of like a hyperbola. So in fact, this integral here diverges, and that becomes a very big problem because this integral, you can check, it converges, and we're saying that this integral has some divergence part, which is not a very good thing to have. So what we really want to do is we want to assign a value to this integral, and in particular, we're going to use the Cauchy principal value. Otherwise, we have some convergent thing being expressed as a divergent thing, which is a bit silly to have. But yeah, I'm not too well versed in Cauchy principal value things, so let me know if that interpretation is correct. But yeah, over here we want to assign a value to this integral, so let's use the Cauchy principal value. So I think you usually put something like PV at the front or something like that. And yeah, notice that this integrand is an odd integrand, and we're integrating over a symmetric interval. So yeah, in the limit, it's still symmetric, it's still odd. So this is going to give us 0. So this is times 0, so the whole thing cancels out. So we find that the integral over psi1 and psi2, both of them together, again, recover I, which is quite nice. So now let's take a look at the integral over psi3 as well as psi4. Now I'll only do probably just do psi4, and the integral over psi3 is very much the same, because it's just on the other side, so you put a couple of negative signs and switch a couple of negatives to positives and so on. But yeah, I'll just do the integral over psi4, and the integral over psi3 is, yeah, it's basically the same thing. Now we want to estimate this integral. We want to show it goes to 0, so let's put absolute values everywhere. What does this equal to? Well, on this psi4, let's introduce a parameterization z is equal to, well, we're going to start at r, and then we're going to go up to r plus I pi. So the real part is going to remain constant, whereas the imaginary part is going to vary, so we're going to have r plus I times t, and we want t to go from 0 up to pi. So this is the parameterization we'll use, and you will notice that dz is equal to I times dt. So let's plug all of this stuff in. So we have the absolute value integral from 0 to pi. Now we plug this parameterization into the function, so we're going to have 2 r plus I times t divided by e to the r plus it minus e to the minus r, and then minus it, and then dz, that's going to become I times dt, and then end of absolute value. Now, this is integrating with respect to a real variable, so we can use the integral inequality to bring these absolute values inside of the integrands. So this is going to be less than or equal to the integral from 0 to pi of the absolute value of everything on the inside. So let's bring that 2 out. Then we'll have the absolute value of r plus it divided by the absolute value of the inside here, so that's e to the r plus it, and then minus e to the minus r minus it, and then absolute value of I is 1, and then we have a dt. Next, we want to bound the top, and we also want to bound the denominator. So bounding the top isn't too tricky to do, because notice what's the maximum that this, I guess, this modulus gets? Well, it's simply the distance from 0 up to that corner over there. But that's just some square roots junk in it. And for large enough r, we can just say that this top over here is less than or equal to 2r, or some yeah, constant times r where that constant is greater than 1. So we have, first of all, this is less than or equal to the integral from 0 to 2 pi, also with a 2 there, of 2r. And then how about the denominator? Well, we're going to use the reverse triangle inequality. What does the reverse triangle inequality say? It says that if we have something like absolute value of a minus b, this is greater than or equal to the absolute value of the absolute value of a minus the absolute value of b. So reverse triangle inequality is something pretty useful when you're trying to bound the denominator. So let's apply it. We're going to take the absolute value of this thing, well, we can split up the exponential as well, so let's probably do that. Absolute value of e to the r is e to the r because that thing is always positive. Absolute value of e to the it is 1. Then we have minus absolute value of e to the minus r, which again is positive. And then absolute value of this guy in here, that's just 1. And then dt. So notice all this stuff that's independent of t, so we can also drag it onto the outside of the integral. So what does this give us? It gives us something like 2r divided by sinh of r. So this in here reduces the sinh. R is positive, so sinh is also positive. And then we integrate from 0 to pi of dt, which is just an extra factor of pi here. And you can clearly see in the limit as r approaches infinity, this is going to turn into 0 because sinh is going to outgrow r. You can use L'Hopital's to show that as well. So this integral over psi 4, its magnitude is bounded above in the limit by 0, so it must be equal to 0 in the limit. So this integral over psi 4 is 0, and then we can do the same argument. We just have to flip a couple positive signs to negatives and so on, and we can prove the exact same thing. It's equal to 0. Okay, and the final integral to evaluate is the integral over little gamma. Let's go ahead and do that. So we have the integral over little gamma now of f of z dz. Now, what is that going to be equal to? Well, little gamma, how do we parameterize it? Well, it's going to be a little semicircle centered about I times pi. So notice z should be able to be written as something like I times pi, and then plus a little circle around it, epsilon e to the I theta. And here we want a theta to go from 0 back to minus pi. So 0 back to minus pi, like so. And of course here you see that dz, that's going to be equal to I times epsilon e to the I theta d theta. So this is the parameterization we want to use here. So let's plug that in. So we have the integral from 0 to minus pi of, we plug this parameterization in, so it's 2 I times pi plus epsilon e to the I theta divided by e to the I pi plus epsilon e to the I theta. Then we also have minus e to the minus I pi minus epsilon e to the I theta, and dz, that's going to become I times epsilon e to the I theta d theta. Okay, so where can we go from here? Well, I'm going to take this epsilon e to the I theta and distribute it into these parentheses. And what I'll also do is I'll bring this I and this 2 out to the front. So this is going to give us 2I integral from 0 to pi of I times pi times epsilon e to the I theta. Then we have plus epsilon squared e to the 2I theta because we combine these two together. And all of this is divided through by e to the I pi plus, and also another thing we can do, we can split up the exponentials as well, just like previously. So we can put e's everywhere. E to the I pi is -1, same with e to the minus I pi. So what happens there, there's also negative in that pi. These are basically gone over here. We can factor out to -1. And yeah, let's just maybe put it out here in the front maybe. And what are we left with? We're left with e to the epsilon e to the I theta minus e to the minus epsilon e to the I theta, and then we have a d theta. So this is quite a bit of a mess with e's and epsilons everywhere, but let's try to take the limit as epsilon approaches 0 and see what happens. Notice that if you take epsilon to 0 on the top, we're going to approach 0 because we have epsilon and epsilon squared here. And also if you take epsilon to 0 on the denominator, you're also going to approach 0. Because yeah, we have, if epsilon is 0 here, then this turns into a 1. This also turns into a 1. We get 1 minus 1, which is 0. So let's use a bit of L'Hopital. So in the limit as epsilon approaches 0, how do I write this? I guess we'll imagine there's a limit out here. But really, this is equal to minus 2i integral from 0 to minus pi. And then we have differentiating the top over here with respect to epsilon, we're going to get I times pi e to the I theta. Then differentiating the second term with respect to epsilon, that's a plus 2 epsilon e to the 2I theta. And then taking a look at the denominator, what happens if we differentiate with respect to epsilon? Well, there's an ei theta constant there, which jumps down. So ei theta, e epsilon e to the I theta. Then again over here, this negative jumps down, so that becomes a plus. Then we also have e to the I theta as a constant, which also jumps down. Then e to the minus epsilon e to the I theta d theta. Okay, now notice we have e to the I theta, e to the I theta, e to the I theta, and e to the 2I theta, but let's just get rid of that 2. And what are we left with? Well, let's now take the limit as epsilon approaches 0. We're going to get minus 2I. Over here as epsilon approaches 0, that's gone. That goes off to 0. And, well, what happens to the rest of everything? Well, as epsilon approaches 0 here, this is going to give us a 1. This is also going to give us a 1. So we have a division by 2. So we have the integral from 0 to minus pi of I times pi, but we divide by 2. And then we have a d theta. So what is this equal to in the end? Well, these 2's are going to cancel, and we get minus I times I, that's negative. So I times I will cancel with negative out here. And we're basically left with pi. And then the integral from 0 to minus pi of d theta. But that's just a minus pi. So this is minus pi squared in the very end. So this was a bit of messy calculations. I'm not too sure if there was a simpler way to do it. And yeah, technically I should have put limits over here as epsilon approaches 0, and yeah, limits everywhere, but we'll just pretend that those are there by assumption. So yeah, the limits of the integral over gamma, that actually approaches minus pi squared. So this overall gives us minus pi squared. So with that, we're basically done with evaluating all these integrals. We know that the sum must evaluate to 0. So what do we have in the very ends? We have 0, it must be equal to 2i, and then minus pi squared. But notice we can solve easily for I, bringing the pi squared over, dividing by 2. That becomes pi squared divided by 2. And that is the final result for today's integral. Now, I guess just as a little something extra, there's actually a real method to evaluate this, which is quite a bit simpler actually. That's just by using Taylor series. So we have I over here, and that's equal to the integral from minus infinity. I think one thing we have to do before that is notice that the integrand is even, because we have odd function divided by odd function. So we can split up the integral so it becomes the integral from 0 to infinity, and then we just have to multiply it by 2 because of symmetry. Then we have x over e to the x minus e to the minus x dx, and then there's an extra 2 out here, but we can bring that to the front to become 4. And what we do from here, I believe we have to multiply everything by e to the minus x, and that gives us 4, integral from 0 to infinity of x, and then e to the minus x over 1 minus e to the minus 2x dx. Now notice on the interval 0 to infinity, this e to the minus 2x is less than 1, so we can turn this into a geometric series. So this is 4, integral from 0 to infinity, x e to the minus x, and then sum running from, let's say, k equals 0 up to infinity of, this is going to be e to the minus 2x, but then we raise it to the kth power, so this is going to be something like k out here as well, and then dx. And now what we can do is we can integrate this thing term by term. You can argue with the real analysis or whatsoever, it's uniformly convergent and so on. So we're going to have 4, the sum running from k equals 0 to infinity of the integral from 0 to infinity of x, and we have e over here. Let's combine these two e's together. Let's factor out to minus x, and we're left with 2k plus 1. So 2k plus 1 goes over here. And now we can do a bit of a substitution. Let's substitute, say, yeah, let's substitute t for x times 2k plus 1. And this is going to give us 4 sum from k equals 0 to infinity of, well, we're going to integrate from 0 to infinity still. If you plug 0 and infinity into here, you're also going to get 0 and infinity. What does x turn into? It turns over t divided by 2k plus 1. And then we have e to the minus. This whole thing becomes t. And then dx, if you differentiate both sides, we get dt equals dx. So dx becomes dt. And then we divide by 2k plus 1. So let's put a squared here. And now finally this factor 2k plus 1 that can basically jump to the outside. So we have sum k equals 0 to infinity of 1 over 2k plus 1 squared, then the integral from 0 to infinity, and I'm going to write this as t to the 2 minus 1, and notice this integral over here, that's precisely the gamma function, but evaluated at 2. But gamma of 2 is exactly 1 factorial, and 1 factorial is precisely 1. So gamma of 2 is 1, so nothing really changes there. And notice this is just the sum of odd reciprocals. And the sum of odd reciprocals, this is a standard result. It's pi squared over 8. This is something you can prove. This is pi squared over 8, so we get 4 pi squared over 8. And yeah, that's basically pi squared over 2. And you can also use this integral to actually prove the sum, because on the one hand, you get the sum, but on the other hand, using complex analysis, you get pi squared over 2. So if you just equate those, this is another way to prove this sum, which is quite nice. So yeah, that's pretty much all for this video. Interesting integral to evaluate. But yeah, if you guys have any integral suggestions, feel free to leave them in the comments or email me. But yeah, up until the next one, have a wonderful day, and I'll see everyone later.